All right, we're back around page 208 in the notes. We're doing polar graphs. We're graphing rose curves, which remember look like a times sine or cosine, n, which has to be a positive integer, and then times theta. So I would encourage you on your calculator or on Desmos or on GeoGebra or whatever to actually play around and change the value of n so it's not an integer. We don't graph those by hand because they're kind of insane, but you get some really nice looking things, and I feel like they should have been called rose curves, but for some reason these that look a lot more like, I think, daisies got the name rose curves. So let's see if we can graph this. So this is going to be a sine thing. So let's see. I did want to mention, I mean, I think I have mentioned this, but it's really hard to say. Uh, the reason that cosine will always have a petal on the x-axis is because cosine always starts at a maximum or a minimum. So like when you're looking at these graphs, you're always starting away from the axis, and then you immediately, the origin, I should say. Well, you're starting away from the axis on the rectangular and away from the origin on the polar. And then what you're going to do is you're going to go toward the origin or the pole on their polar graph. So you're always going to start off with that half of a circle, half a petal, not half a circle. Jeez, they're not circles. So I just wanted to make sure that I had mentioned that. Now that I mentioned it again, I think I did mention it, but all right, we start these the same way all the time. So 3 petals, because n is 3, which means I need 6 increments. So the period is going to be 2 pi divided by 3. So an increment is going to be the period divided by 4, so 2 pi over 12, which is pi over 6. So 6 increments is going to take pi. And you'll notice a pattern there. I'm not going to tell you what it is. There's a pattern between even number of petals, odd number of petals, and how long it takes. You can pretty easily work it out. So work it out. All right, so 2 pi over 3, and then pi over 3, and then this will be, these are pi over 6s that we're counting by. In this case, we actually don't need to know those, fortunately, so I don't have to go back and like relabel and bemoan the fact that I have not yet done that. 3, -3. All right, here. That's going to be 1 petal. That'll finish 2 petals, and then that'll be 3 petals. So this in the rectangular graph is kind of the rectangular picture of 1 petal, and then our second petal, and then our third petal. So sine is a little more satisfying because you get to do like a full petal to begin with instead of half a petal and then everything else and then finish the petal. But it's also a little weirder because you start at the origin, you sweep out. So let's actually graph this. So we're going to need to know when r equals 0 because that's the tangent lines. And you can see those on the graph. So theta is going to be 0, and then pi over 3, and then 2 pi over 3. And then back at pi, but pi and 0 are the same, so I'm not going to bother to list that. So let's graph those in a sort of obnoxious color. I don't know, it's not really obnoxious, but well, geez. Horizontal lines, man, they're hard. Let me make it even bigger. It's easier for me for some reason if I start at the origin. I guess it's like I'm used to writing from left to right, so that's like, I'm going to pretend that that's the reason that it's easier. And then pi over 3. Then pi over 3, of course, is also 4 pi over 3, because if you go straight through, you'll end up at 4 pi over 3. And then 2 pi over 3. I think in general, it's just easier to go toward the origin than it is to start at the origin and go out. I don't know why that would be. Some kind of weird psychology thing. Also, maybe it's not the same for you. I have no way of knowing. All right, what are we going to count by? So 3, I'm going to count by 1/2, I think. So it's going to go 1/2. This circle here is 1. This circle here is 2. This circle here is 3. All right, so let's put in a target, right? By the time we get to pi over 6, which is what this is, so maybe I will bemoan that I didn't label everything. By the time you get to pi over 6, you have to be up at r equals 3. So let's put a point there as a target to aim for. So there we go. All right. Now, what do? Look at the rectangular graph, and you can see, let's do a little shading action on this. Here, maybe small. All right, hopefully this works. Start at 0, and you're going to increase until you get to pi over 6 when you're at a maximum of 3. So on the graph, I'm going to start here and go until there. So you can plug in values and get more points, right? So sine, you kind of want to end up with pi over 6s. Those are like the ideal thing to do because the sine of pi over 6 is nice. What I usually do, I just look for the general shape on these. I'm not super obsessed with making sure that everything is the exact right thing in between. The maximums and minimums, I try to nail those, but everything else, you know, you do your best. And then I can't use that color again. So we're going to come back here. So by the time we get to pi over 3, we have to be back at 0. And there you go. And then if you go in along a tangent line, you come out along a tangent line. So by the time you get to this, which is going to be at that's actually pi over 2, right? So let me just go through and finish labeling things. Pi over 6, 2 pi over 6, 3 pi over 6 is pi over 2, 4 pi over 6, which reduces 5 pi over 6, which does not, and then 6 pi over 6. Okay, so now we can just like go for it, right? By the time you get to pi over 2, you have to be at -3. So -3 is going to be down here. So that's what we're going to aim for, right? Go in along a tangent line, come out along a tangent line. Like this. And then, so, you know, you're going to swing back in. So that part of the graph that we just did was this part. And now from pi over 2 to 2 pi over 3, you're pi over 2 to 2 pi over 3. So you're rotating here. But since r is negative, you're graphing not in the second quadrant, you're graphing in the fourth quadrant. So we're gonna, but once you get the pattern down, you just kind of go with it. This. And then by the time I get to 5 pi over 6, I'm going to need to be up at +3 again. So 5 pi over 6, I need to be at 3. So that's that. If you go in along a tangent line, you're going to come out along the tangent line and go like, oh, I went past the line. It's tough. Like that. And then finally, I mean, you can just finish this by symmetry or logic or whatever you want. Okay, so we get that. I've been neglecting to do this on the previous graphs. What I'm going to do is I'm going to label the like maximums and minimums. Okay, and I'm going to label them correctly in polar. So this point, I'll do it in a weird color. Well, I don't know about a weird color. I'll do it in some different color. Let's use this. So the first time we get here, this is r is okay. Don't do it. And now I got to redo something. That is so frustrating. This app, for whatever reason, oh, now it's like frozen. Oh my gosh, hold on. Come back. Okay, this app, I love it. It doesn't have a redo button. Like, what in the world? Who would ever make an app that doesn't have a redo button? All right, so this point, I forget what color I was going to use. I'm just going to use red. R is 3, theta is pi over 6. Okay, that's good. Now the next key point that we got to, R is actually -3, and theta is pi over 2. So you can't really tell when you're looking at a polar graph. It's very hard to tell like what value of theta put us at this point, because you know, coterminal angles will put you there, or it could be an angle that differs by pi from what you're expecting, and r is negative. Very hard to tell. Then when we got here, it was 3 and 5 pi over 6. All right, and we got that. I really want to go back to the previous graphs and do that. Should I do that really fast? I'm not doing it on that graph. That's crazy talk. I'll do it on this one. So this was 5, 0. And then we go around and around, and this will be -5, 2 pi over 3. No, pi over 3. You can actually read them right off of the rectangular graph. And then we go around and around, and this will be +5, 2 pi over 3. And we're done. So if you look at the points on the rectangular graph here, so this point is definitely 5, 0. This point is pi over 3 and -5. And then this point, which is already highlighted, so I'll highlight it above, is 2 pi over 3 positive 5, but then when you write them in polar, you switch r and theta. So like, you can read them right off the graph. I should have mentioned that a long time ago, but I forgot. So let's do the next one. All right. We're gonna start off by graphing, well, by thinking, how many petals, right? So here, it's even, so we're gonna get 4 petals. And then after we get 4 petals, we'll need 8 increments. Let's say therefore 8 increments. All right, now what is the period? Period is 2 pi over 4, which is pi over 2. The increment is going to be the period divided by 4, so pi over 8, and that's terrible. It's terrible, but it's not like the end of the world, I think. Unless, did I do this wrong? 2 pi, yeah, I did that entirely wrong. Hold on, hold your horses. None of this is right. Not like literally none of it, because I divided by 4 for some reason. I did because of the petals, that's what it was. So the period is 2 pi over 2, so pi, and then pi over 4. This feels better. It feels better because I knew what the graph should look like, and I knew that that just wasn't right. All right. So there's actually it's always advantageous to know what the graph is going to look like, which is the most backwards thing to tell someone who's trying to learn. But like, once you learn it, learning this will be so much easier. That's basically what I'm saying to you. All right, we need 8 increments, which means we'll need 2 full periods. So we'll go to 2 pi. And again, is there a pattern there? There is a pattern. Even numbers, even values of n, odd values of n. Pattern. Think about it, find it. It's staring you right in the face based on these last 2 problems. All right, so cut and cut, cut and cut. Make sure you are good at graphing these, because graphing these in rectangular is the key. So this is our r-axis, this is our theta axis. I'm a little cavalier about labeling those, like more so than I should be. Here to here to here, here to here. You need to hear me say here every time. So here, 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 and there. All right, let's sketch it in. That'll be 1 petal. This will be 2 petals. This will be 3 petals. This will be 4 petals, and we're expecting 4 petals. All right, so what makes r equal 0? You can see it on the graph. It's pi over 2, pi, 3 pi over, this is really nice, and then 2 pi. It's the quadrantals. So actually, this graph potentially, so now I'm feeling the most pressure. This is the easiest graph we're going to make, because it's the quadrantals, and then the petals are just going, it's really going left is hard. The quadrantals and then the petals just cut the quadrants in half. So those are your pi over 4s. So we can knock this one out pretty quickly. All right, so we got to get out to 7. How many circles are there? 1, 2, 3, 4, 5, 6. There are 7. Okay, so we'll call this 7. And we'll just go with it. All right, by the time I get to pi over 4, I need to be out at 7, and I'm just going to sweep out as I go. So here I go. Here I go again on my own. And then we're going to sweep back in. And then, okay, so what's going to happen is in the second quadrant for theta values, the second quadrant of theta values, which is here, r is always negative because you're below. Since r is always negative, instead of drawing in the second quadrant, we draw in the fourth quadrant because you always go in the adjacent quadrant. So here, adjacent, that's not right. The diagonal quadrant, I guess, is the potentially right way to say that. So I'm going to aim for this. So at this point, it looks like it's happening at 7 pi over 4. It's not. It's happening at 3 pi over 4, but r is negative. So go for it there, and then back in. That was a little weak. Should I do it again? Sure. I can't do it right. Okay, hopefully you get the idea. And then by the time we get to, this is 5 pi over 4, r is going to be positive 7. So we're out here. Really, the bigger the leaves are, the petals, bigger the petals are, the harder it is to draw. It's like it would have been easier to make this if we had just said like 3 circles out, we're calling that 7. You're counting by 7/3 for some weird reason in life. but we didn't do that. In along a tangent line, out along a tangent line. These always remind me of gravity wells. Gravity well? I don't know if that's the right thing. Uh, so like maybe you've seen these. I think I saw one at the Smithsonian once, or like Liberty Science Center or something, where like it's this like giant circular thing, and you put a coin and you like roll the coin, and the coin just like just keeps rolling around. Eventually, it'll make it to the middle, but it takes like forever. It's also like a really popular YouTube video that's something like that. Can't think of it right now, but look it up. I think it's called Gravity Well, maybe potentially. Um, but like once you start your motion, you just keep going, and it wants to go counterclockwise, and it just wants to keep following the path that it's on. So like you don't get a lot of sharp turns with polar curves. All right, let's label these up correctly. So this is 7. Let's use a different color. Let's jazz it up. Let's not use that color because that's the color that I keep using for the tangent lines. So here we go, 7 pi over 4. All right, and then you follow through, right? And you end up here, -7 at 3 pi over 4. So that's surprising. That's a surprising result. And then you keep going and you end up at +7 when you're at 5 pi over 4, which is fine. And then you keep going and you end up at -7 when you're at 7 pi over 4. So surprising result. You can't really tell what the point is just by looking at it. You like have to know the equation or have some sense of it, right? There are many ways to write the equation for this graph. You have to know the one that you're dealing with to know when you got to each of these points. It's like a big deal. So it feels very parametric if you've done parametrics. If you're in my class, you definitely did. It feels very parametric because of that. All right. My question to you before we even really do this, is this a rose curve? I mean, it sort of fits the bill, but it also fits the bill for something else that we've done. So here, n is equal to 1. So there should just be one petal. A rose curve with one petal? So then the period is 2 pi, I guess pretty clearly. And then, but if it's one petal, we only need 2 increments. We don't even need the full period. Pi here to here, here's pi over 2. So it's negative sign. So it'll be like here, 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 and here. I guess I should label this as 4. This is -4. While we're labeling, I should probably label that this is the r-axis and the theta axis, which I'm aware that I forget almost every time. Here. Okay, so that's your one petal. That's going to be the entire thing. And then this is the thing that will screw you up in calculus, in Calc 2 specifically, and then also in Calc 3 later on. This only takes 0 to pi to trace out, this curve that we're about to get. So what is this thing? So I'm going to dot in my tangent line, which is 0 or pi, depending on which one you want to use. So here, or, you know, you could think of it as using both of them, really. Okay, so that's my tangent line. This is weird. So what I'm going to do is I'm going to rotate from 0 to pi over 2. So I'm going to rotate this way. By the time I get to pi over 2, I need to be at -4. So I'm going to say that this is like 2 and this is 4. So by the time I get to pi over 2, I need to be at -4, which will be here. Now, what is happening? What's happening is, what is this thing? This thing is actually a circle. This is a circle. We know what this is. R equals -4 sine theta is a circle tangent to the origin with a diameter of 4. Oh man. The first thing is an abbreviation for width. It's W with a slash. Didn't work out very well. And then I tried to abbreviate diameter with a diameter of 4, and it's on the negative y-axis because of the -4. So actually, what can we do? Well, I can kind of dot in. I know that if I go like parallel to the y-axis from there, and then also from here, and then if I go perpendicular, well, perpendicular y-axis are really just parallel to the x-axis. From here, I can actually find 2 points that are on this circle, right? because this is the rectangular point, 2, -2. And this is the rectangular point, -2, -2. So I need to go like, so initially you want to draw here, but since r is negative, you end up drawing here in this sliver. So we're going like this, quarter circle, quarter circle, quarter circle, ooh, kind of, and then there. All right, so that's the graph we're going to get. So it's sort of an open question. I mean, is this a rose curve? It fits the definition of a rose curve for sure. Are all circles rose curves? I'm going to say no to that. Are all of the circles that are tangent to the origin and have their center on one of the coordinate axes rose curves? I think yes. I think they fit the definition of a rose curve. All right, so we did a lot of graphing with rose curves. There are other videos on the channel. If you easiest way to find them is probably to like just search the channel or to go to my webpage, Turk's Math Stuff, which if you've noticed is at the bottom of every single page of notes. Go there and click on Note 16 and then choose the playlist for it. And there are more examples of graphing these things. So you might want to do that. I'm going to end this video here and I will come back and see you in the next video. So I hope you are finding this kind of helpful. And stop.